Welcome to class, ladies and gentlemen. Mr. Eicher here, but not here. Well, today I am away, but I thought I would do my best to teach you the lesson digitally. Oh, I have my jumping thing at the bottom of the screen there. I don't think I'll be able to avoid that. Oh, I should get started. So, our lesson today has kind of two main topics. The first topic that we're going to see is solving equations, and we've solved equations like this before. Today we're just adding what type and number of solutions there are, which we've actually done that before too. So hopefully these first couple will be a nice review for you. And then we'll do some more of those right here, 7 through 10. Probably the hardest part, the part that you just have to get used to, is this last part of class, the second part of class, called Descartes' rule of signs. Rene Descartes was a French mathematician in the 1600s. He was also a very important philosopher who somehow, it's crazy, I looked at a proof of this and still don't think I quite understand why it works, but I'll show you how it works. But he came up with this observation to help us determine how many real number solutions there are. I should really close that somehow, I'm not sure, but anyway. So at the beginning is kind of a review question. I'm not going to take time in this video to go over that, but notice it says use synthetic division, or synthetic substitution, which is a lot like synthetic division, to plug these values into the function, the f of x function, and then you'll plot the graph. The various descriptions here, we would just like to know, since it's an even degree polynomial, what will the graph look like? The leading coefficient is 1, what will the graph look like? And those sorts of questions. So I'll let you do that on your own time. If you'd like to pause this video and take, I don't know, 5 to 10 minutes to complete that, you could do that. But I'm going to move on. So we have something called the fundamental theorem of algebra. Sounds very important, fundamentally important. We've kind of been alluding to this throughout this chapter, but this says every polynomial equation with degree greater than 0 has at least blank root in the set of complex numbers. Now this might sound like a strange theorem, but it says every polynomial equation with degree greater than 0 has at least one root. There you go, see how well I can write on this. One root in the set of complex numbers. So for a polynomial equation as simple as like y equals 3x plus 1, that would have at least one root, and if you graph that you'd get something like this, and there's the one root. If you have something like a degree 2, y equals x squared or some such thing, maybe we'll do x squared, running out of space already, poor planning. That would be a parabola like this, and it has at least one root, and it actually has two roots. Now don't get freaked out. Now I'm just going to do a little highlighting here. Don't get freaked out by this one root in the set of complex numbers. Remember, complex numbers are both real number solutions and imaginary number solutions. So yes, we do get to do some imaginary number solutions today. The corollary to this says a polynomial of degree n with complex roots has exactly n roots in the set of complex numbers, including repeated roots. Repeated roots. Or I also call them double roots, those that kind of bounce off the axis. And some other types too. So what this corollary says is a polynomial of degree n with complex coefficients has exactly n roots. We've been talking about that through this chapter as well. If you have something like y equals, oh, that's really thick font, y equals x to the 7th, then at most it can cross the axis, oh boy, it can cross the axis once, twice, thrice, 4th, 5th, 6th, 7th. It can at most cross the axis 7 times. Oh, get my little highlighter going on. 7 times. Now, if it doesn't cross the axis 7 times, there's still exactly 7 roots, but some of them might be imaginary roots. And we'll talk a little bit more about that later. So now I get to try to erase all this. Let's see, what button is that? That one. Look at that, how nice that is. So, graphically what we have, let me get out of this screen. Graphically what we have, we've kind of done this before. Make this a little bigger. There we go. How many zeros do the following polynomial functions have, and what type are they? The easy ones to see would be this one is a 0, and this one is a 0. So that's 2. Now you can observe that it's not a quadratic function. It doesn't look like a u, a parabola. But on the edges, it kind of looks like a u, a parabola. So we just have to deal with these other solutions over here. Now they don't really cross the axis, but it does tell us that it must be bigger than a degree 2 polynomial. So we would guess that it actually has 4 solutions. It's probably a degree 4 polynomial, where 2 of the roots, these 2 that we can see, 2 of the roots are real number solutions, 2 real roots, and the other 2 would be imaginary number solutions, for a total of 4 complex number roots. Again, remember, a complex number contains both the real numbers and the imaginary numbers. So let's look at the next one. Notice we can count 1, 2, 3, 4. We can count 4 solutions. And this appears like it would be a degree 4 polynomial. So in this one, we would have 4 solutions, and they would be 4 real number solutions. 2 of them are positive, and 2 of them are negative solutions. The next one, notice we have this shape. It's going in opposite directions. So this would be an odd degree polynomial, odd degree. And we could count some of the solutions. Maybe we'll do that in purple. 1, 2, 3. I kind of missed there, but they're over here somewhere. So there's 3 real number solutions, crosses the axis at 3 times. Now we need an odd degree polynomial. Now there's a lot of stuff going on right here. Okay, that circle didn't really work the way that I planned. I'm going to try it again. Okay, that basically circled the whole thing. But you have a lot of bumps in the middle there that you have to deal with. You have to figure out. So there's a lot of writing on the screen. Let me get rid of this. So we know we have at least 3 real number solutions. One way that you can help yourself out is count the number of times, the number of directions it has. So notice here it goes uphill 1, downhill that's 2, uphill in the middle there, downhill, and then uphill. That's 1, 2, 3, 4, 5. So our guess would be it's going to be a degree 5 polynomial. So that means if there are 3 real number solutions and there are 5 total solutions, there must be 2 imaginary solutions. So how about you pause this video and see if you can do number 4. Just work with your neighbor on number 4. Which looks like this. On number 4, we can see we have these going in opposite directions, so it's going to be an odd number of complex roots, complex being real and imaginary. We have 1 real solution, And notice we have a turn down here, and we have a kind of a weird thing going on over here. Kind of it keeps increasing, but then increases at a slower rate, kind of strange over there. So rather than guessing that it's a degree 3, because of this weird thing going on, there's probably some extra roots or solutions here. So rather than saying 2 imaginary, maybe I'll do question mark. It might be a better guess to say there might be 4 imaginary solutions. So 1 real and 4 imaginary. This might be a degree 5 polynomial rather than a degree 3 polynomial. Again, mainly because the weird stuff going on in there. If that weird stuff wasn't going on, if it was pretty smooth, just like this, then that would most likely, well, that would be a degree 3 polynomial. So let's solve some equations. This next part of class should be really similar to what we've done before. Let me just, no. Okay, so solving the equations, state the number and type of roots. Number 5, it looks like a quadratic. So we're just going to try to factor this. I'm going to do a little guess and check. It actually might be a perfect square trinomial. We have x minus 4, x minus 4, and to check that would be negative 4 gets to negative 8, and multiplying them gets to positive 16. So that looks good. So we have x equals 4, x equals 4. Notice this is a repeated root or a double root. Repeated or double. So based on the degree, oh, can't really see that anymore, can you? Based on the degree, you would expect 2 roots. So we have 2 real number roots, but it was a double root or a repeated root. So if we were to graph that, it's going to be a parabola that touches the axis just at one place and then bounces off the axis. And we've seen that before. So state the number and type. That's 2 real number. Real is the type and 2 is the number, and they're repeated solutions. The next one, we should probably take a greatest common factor out first. So we get to this point. And then we set both equal to 0. We have x equals 0. This is the 0 product property. X squared plus 4 equals 0. So here's one of our solutions. X equals 0. Crosses the axis at 0. X squared minus 4, to solve that, it's not really factorable, but we could do x squared equals negative 4. Subtract 4 from both sides. Square root both sides. Yeah, you like that? You like that? Is anybody hollering at the screen? Don't forget the plus and minus. Oh boy. 2 solutions. Positive square root negative 4 and negative square root negative 4. Now I hope you remember that the square root of a negative 1 is I. So this would simplify to be plus or minus square root of 4 is 2. Square root of negative 1 is I. So there's 2 other solutions. This is what we would expect. Noticing the degree of the polynomial, x cubed, that's odd. So we would say we have 1 real number solution, that's 0. And we have 2 imaginary number solutions. That's these guys down there. Positive 2i and negative 2i. So what might this graph look like? This graph might look like it's going to pass through 0, and then it's going to turn but not cross the axis. So because of our 2 imaginary number solutions, it could look something like that. It could also just look like, this is getting really messy, but it could also just look like could look like that, but probably more likely that it looks like that with some kind of weird turn in there. So really, on this page 5 and 6, we've done stuff like this before. Hopefully it's nothing new. The only new part is stating what type and number of solutions there are. But even that, we've kind of done that before. Turning the page, number 7. Predict the number of solutions. I see a x squared, so I'm going to predict there are 2 solutions. Solve the equation. I'll do that in a second. And then state the number and type of solutions. Now, I don't know about you, but looking at this one, since that 1 is there, we're probably not going to be able to factor. Factors of 1 times 1, that add to -5. I don't know. So I'm going to use the quadratic formula. So solving this, we would have the opposite, so x equals the opposite of b plus or minus the square root of b squared, that's 25, minus 4 times a times c, so that's just 4, over 2a, 2 times 1, 2a. Simplifying that, we get 5 plus or minus the square root of 21 over 2. Square root of 21 doesn't have any factors that we can factor out. So it looks like these are our 2, and they would be real number, particularly irrational number. 2 irrational number solutions, which should make sense. A quick graph, it probably is just going to look something like that. Just a regular old parabola. How about you pause this video and see if you could solve number 8. Voila! The beauty of technology. So I factored to get x minus 3 equals 0. We get 3. It's a double root. It would be a parabola touching the axis, bouncing off the axis at one place. So we have 2 real solutions, but they are repeated. It is a repeated root, or double root. And I would have predicted that. We get an x squared here, so we should get 2 solutions. Number 9, notice each term has an x, so you should probably take a greatest common factor out first, and then try to solve. It may or may not be factorable, so you might need to use the quadratic formula or completing the square or some other method like that. So why don't you pause the video and finish number 9. Voila! So it was factor the x out on this first step. That gives us one solution, x equals 0. Setting the other equation equal to 0, this part of the equation, I noticed that 13 is prime, so its only factors are 13 times 1. There's no way you're going to get to a 4 with the 13 times 1, so I just used the quadratic formula. You could have completed the square, I guess. That probably would be easy enough, but quadratic formula it is. Plug the values in here. Hopefully I did that right. You double check my work. Subtracted, I got a very nice negative 36 for the discriminant. And then the square root of negative 36 turned out to be a very nice 6i. And then they're all even, so divide by 2, and I got 2 other solutions. There's a negative plus or minus there. It's just a little hard to see on the screen, plus or minus. So we get 3 solutions. Hopefully you predicted that based on this right here. It's an odd degree. We get 1 real number solution, which is 0, and we get 2 imaginary solutions, the 2 plus or minus 3i. The last one we have is number 10. So again, why don't you pause this video and complete number 10. Notice it has a x to the 4th, so you should be looking for how many solutions. You should be looking for 4 solutions. So pause this video. Perhaps you tried this approach, add 81 to both sides, and then take a fourth root, meaning what times what times what times what is 81, and I believe that is a 3. Notice I have a little 4 up here for fourth root, not a square root. But the problem here is that I'm missing something, aren't I? I only got 3 solutions, but I'm expecting to be able to find 4 solutions. So rather than doing it this way, perhaps if we could factor this to be x squared times x squared to get x to the fourth, minus 9 plus 9 equals 0. This is a difference of 2 squares. Now this part right here, this part, would give us x squared equals 9. X would be the square root of 9 plus or minus the square root of 9, which is that original solution I got, plus or minus 3. The ones that I missed, however, were this second, this little dividing line, was this second piece where I have x squared equals negative 9, x equals plus or minus the square root of negative 9, which would be plus or minus 3i. Those are the ones that I kind of couldn't observe by the first approach that I used. So notice now I have 4 solutions. I have 2 real number solutions, and I have 2 imaginary number solutions. So I found all 4. That was the first part of class. The second part of class, we're going to be looking at that Descartes' rule of signs. Before we get to Descartes' rule of signs, something you may have observed that on the previous solution, notice that we had 2 imaginary solutions. Complex zeros always come in pairs, and they are conjugate pairs. So if one of the zeros is a plus bi, then its conjugate, a minus bi, is also a solution. And that's going to be very helpful in the future as we work on these. So for this number 11, give a second 0. If 3 plus 7i is a solution, then 3 minus 7i, its conjugate, is a solution. And then b, the conjugate is negative 5 still. Don't switch that sign. That's a common mistake students make. Just switch the sign on the inside with the imaginary part. So those are also solutions. Now let's look at Descartes' rule of signs. The last part of class, not a lot of complicated math that we have to do, but a lot of focus and counting. So if you can count positives and negatives, then you could do Descartes' rule of signs. So let's look at that. So Descartes' rule of signs, again, Descartes is the mathematician. Descartes' rule of signs help us determine how many positive and how many negative real number solutions there are by looking at the function. Now this is pretty amazing that he was able to discover this. So consider this function p of x right here. Descartes' rule of signs says this: the number of positive real zeros is the same as the number of changes in sign from positive to negative or negative to positive, or less than that by an even number. Now that's a mouthful, but it's very easy what it's actually saying once I explain it to you. So notice we have a negative 3, and then it changes to a positive 8. That's 1. I'll just keep my tally over here. That's 1 sign change. And then we have positive 8 to negative 4. That's another sign change, another tally, tick mark. And then we have negative to a positive 3. That's a third sign change. So how many positive real zeros are there in this function? Positive ones. So right of 0, positive real number solutions. We would say there are 3 or less than that by an even number. So you're always going to be subtracting 2 from the answer you get. It's either 3 or 1 positive real solutions. So what that means is this graph, it could look like this and cross the axis 3 times on the right. So that's 1, 2, 3 positive real solutions. Or it could look like this and cross the axis once. let's say like that. Now, I didn't really make the leading coefficient the right direction, but ignore that for now. So the positive real zeros is the quick one with Descartes' rule of signs. The number of negative real zeros, let me clear the screen so you can see a little better. The number of positive real zeros, pardon me. The number of negative real zeros, I'm on the next part. The number of negative real zeros. Now you have to do a little plugging in a value. We're going to do the same process, but you have to change this and plug in a negative x for each one. So if you plugged in a negative for each of these x's here, how would that change the signs? Well, that would be negative x cubed. The negative is going to stick around because you're cubing. A negative times negative times negative is still a negative. So that would make it a positive 3x cubed. And then if you put a negative in this term right here, the squared is going to get rid of the negative. So the sign stays the same. See that? Positive 8x squared. And then this last one, this one right here, negative 4x. If you put a negative in for x, it's going to change the sign, so it's positive 4x, and then plus 3. And then we do the same process that we did before. How many sign changes are there? It goes from positive to positive, that's not a sign change, that's the same, to positive, that's not a sign change, to positive, that's not a sign change. So we know that there are exactly 0 negative real solutions. So earlier we said there's either 3 positive or 1 positive. So using a little bit of logic, since this is a degree 3 polynomial, since this is degree 3 over here, we know that it will either have 3 positive and 0 negative, that's a total of 3, or if it has 1 positive and 0 negative, do a little math here. How many imaginary solutions must there be? 3 total solutions, 1 positive, 0 negative. That means there must be 2 imaginary solutions. Now, Descartes' rule of signs is pretty cool, but it doesn't tell you what the solutions actually are. It just helps you narrow down your search for what are the solutions. So let's look at number 12. Let's find the positive real zeros. So we're going to count positive 5 to positive 8. That's nothing. Positive 8 to 1, negative, okay, that's 1 sign change. And then negative to positive, that's another sign change. So we would say for the positive reals, we would have 2 or less than that by an even number, or 0 positive. A little plus sign for positive real solutions. For the negative, plugging in a negative for the x, we would have negative 5x cubed. The sign would change because the negative. Plugging in a negative for the next term, that would still be just positive 8x squared. And then plugging in a negative here, that would be a positive 4x, and then plus 3 doesn't change. So how many sign changes do we have? We have 1, negative to positive, so that's 1. This one doesn't change, and this one doesn't change. So we have 1 negative solution. Now notice we can't really go like 1 or negative 1 negative solution. So this tells us there must be exactly 1 negative real solution. And then kind of logically, it could either be 2 positive, or 1 and 1 negative. 2 positive, maybe I use a comma, 1 negative. That's the possibility. Or you could have 0 positive, 1 negative solution, and then how many imaginary solutions? That would be 2 imaginary solutions. Why 2? Because our degree, it is a degree 3, so there must be 3 total solutions. So on this first one, that would be no imaginary solutions. So why don't you try the next three. I will stop talking this video because it's already long enough. Try the next three, and then you can begin the homework assignment where you're going to be practicing this skill there as well. Thank you for your attention, and enjoy your day.